So our next speaker is Richard Steenbergen from nLayer, and he will address the 10 gig pluggable technology. You should be.
Where's the?
Yeah, just close it here. And you are right here.
Ooh, this is the old version. I sent in the update. It's on the website. But,
Okay. Just one moment.
Yes.
Valerie, do you have it? Do you have it on the?
I don't. I thought it was up here. Richard Steenbergen with nLayer Communications. I have to start by thanking Todd for the donation of the slide set. If I don't mention it at least 2 times in Anog, my Renesas account mysteriously breaks. So thank you, Todd, for the donation of the slide set. I kind of waffled back and forth here for a little bit as to whether to talk about all 10 gig or 10 gig E. The title is 10 gig E just because there's a small portion of it where I didn't feel like really talking about the entire spectrum, but a lot of this applies to 10 gig in general, so OC192, fiber channel, various other 10 gig technologies. So, quick review. What are pluggables? Is what we're talking about. Basically, we're talking about those little transceivers that you stick into routers that are used to transmit or receive a signal. So for anyone that doesn't know, they're little hot swappable things. They're capable of operating many different types of physical media. You can drive copper with them. You can drive signals over many distances of multi-mode, different kinds of multi-mode, single mode. You can do 10, 40, 80 kilometers. You can do 100. There are people that are making 120 kilometer optics. There's a standardization of these things so that you can interchange them among vendors. Well, actually, the standardization is so that the vendors can interchange them among themselves, not so that you can do it, but we'll get to that. The benefits of using pluggables, basically, there's a bunch of technical benefits in that you can easily accommodate whatever media type you want. So when you start buying a high-density card, if you buy a 48-port card, you don't have to buy 48 of a short reach, 48 of a long reach, anything like that. You can mix and match with whatever type you want. And the other major technical benefit is the easy replacement in the event of component failures. So I don't know how many people here have ever worked with fixed optic cards where one of the ports goes bad, but I've worked with them where all of the ports eventually go bad. So it's a big help. And then obviously there's the financial benefits, and that there's a pay-as-you-populate model. So you might start off only needing 5 ports in a given pop. You're still going to buy and deploy a 48-port card maybe, or whatever the case may be. In the case of 10 gig, you might only need 1 port on a 4-port card, something like that. The pluggables are reusable, so as you upgrade your cards, you might have started out at the 1 gig level with an 8-port SFP card, and that became a 16, and that became a 32, and that became a 48, and you might still be using those same pluggables across different systems. So a lot of your investment is protected. And also the cards are reusable. So say, for example, you were using one particular media type, which is, something comes along, there's a newer standard, better standard, you just swap out your optics, and now you don't have to reinvest in the cards. And obviously, anytime you have standardization, you have competition, and that's going to bring the cost down. So pluggables are standardized, obviously for good reason. It's so you can have interchangeable components and mass production. And the standardization is achieved through a vendor MSA, which stands for a multi-source agreement. And it's basically just a group of vendors that get together and say, this is the specification of the product that we're going to make, and we're going to sell this to multiple vendors, and then multiple hardware routing network switching vendors are able to buy their pluggables from multiple sources. And typically the specifications for this are published under what's called the SFF. There's a website where you can go and download all the specifications and see all the exact details of physical, electrical, mechanical, the management interfaces, serial interfaces, et cetera, power, whatnot. Quick review on first generation pluggable technology. We started out in Ethernet land with the Xpack, which was actually originally designed for fiber channel. It had nothing to do with Ethernet at all, but the Ethernet people said, hey, it's a good idea, and it only requires 0.2 gigabits more to signal our our 1 gig, and that quickly became popular. And that was very common to find on gear from 1998 to around 2002. And it's still used today. There's nothing wrong with it. It's just a little bit larger. Around 2002, they first started shipping the SFP, which is just a smaller version, and it actually does a couple things. It's multi-rate, so you can use the same pluggable for a 1 gig, 2 gig fiber channel. You can use the same pluggable in Ethernet, and now these days it's almost impossible to find one that you can't also take the same pluggable, put it in an OC48, and run it that way. And these days, for a few dollars more, you can get the ones that are also do 4 gig fiber channel. And if Ethernet cared, they could do 4 gig Ethernet over the same type of thing. But these are very flexible optics. And the other notable thing about SFP is it first introduced the digital optical monitoring, which we'll talk about more later, but it's very handy. And these days, the current standard for 1 gig, you're going to see a 48 SFP card density. So back in the 1 gig E, even going up to OC48, you only had a few choices. It was Xpack or SFP, and for the most part it was SFP, and that was that. The problem with 10 gig is there's a whole bunch of choices out there. And some of these are more viable than others, but technically there's 1, 2, 3, 4, 5, 6, 7 of them. Some of them are less well known than others, but each one has its own back-end design, and each one has its own pros and cons. Lots of choices to pick from. And a lot of the problem in the operator community is figuring out what kind of equipment they want to buy, what kind of optics they want to support, how they want to manage sparing, how they want to manage the different features and advantages and disadvantages of the optics. So I have a little thing, if anyone reads like Engadget, it's the little thing that they use to compare cell phone sizes. I almost left the iPhone in for reference, but there was a limited number of entries you could put in. So This kind of gives you an idea of what the physical size is of these things. And I left off some because they're either too big or there was a limited number you could put in. But you kind of see in blue the Zenpack, the X2. The colors are a little off, but the middle orange-yellow thing there is the classic GVIC, the XFP, and then the SFP. So it kind of gives you an idea what you're looking at size-wise. So a quick review of the different technologies out there. The very first thing for 10 gig was called the 300-pin MSA. It was very large, and it actually wasn't even a pluggable. It was a snap-on connector. It drew a lot of power. It had a very high-density, low-speed interface, which was key for working with the technology at the time. And obviously, that kind of a format is suited to a first-generation technology. You're making use of the existing bus capacity that you have, the existing interface speeds. And in fact, we're still seeing the same kind of thing used today for 40 gig 300-pin MSA. But if you're still using these for 10 gig, very, very sorry. I have a pile of these in my basement if anyone wants them. The next standard, and probably one of the most, if either the most popular or second most popular, is the Zenpack. So this was an MSA founded in 2001. It features a XAUI interface, which is 4 channels of 3 gig talking to the system. It has a max power use of 6 to 10 watts. And when I say max power use, what I mean is there's different power classes. We'll talk more about that later. But in terms of maximum draw, those are the classes. So you are looking at a maximum power use of between 6 to 10 watts. The 5-framer is on board. I'll go into more detail on this. Just a quick overview. It's very widely deployed, and it has a very wide selection of exotic optics. What I mean by exotic optics are 80-kilometer reach, 10 gig optics, DWDM tuned optics, anything that's out of the ordinary, that's out of short reach stuff that you might find anywhere, is very widely supported. And it's also very popular among enterprises because CX4, LX4 support. So then there's the X2, which is basically an evolution off of Zenpack. Electrically, the connectors are exactly the same. So anything you can say about Zenpack, you can say about X2, except it's smaller and draws a little less power. But it's the exact same thing, the exact same hardware, implemented the exact same way, but you can get a little higher density out of it just because it's physically smaller. And it's not very common right now. So far, the only major adopters are Cisco and HP. And you can make the argument that if Cisco's pushing it, that by definition it's a major deployment, but it's only in a few new products, and I've kind of seen lukewarm support for it from a lot of operators. So right now it is very limited, and the choices on exotic optics are almost none. It's been pointed out to me that there are third parties that sell some 40-kilometer DWDM tuned versions of this, but if you bought a Cisco product, you can't buy it from Cisco, so by definition, it's not supported officially. There's also the Xpack. I didn't even bother to look up when the MSA was founded. It wasn't immediately clear. It's actually very similar to the X2. The only difference is kind of the physical form factor. It uses LC connectors. You can see it's a little bit smaller there. Basically, this was designed for use on PCI cards. Back in around the same time as X2 and everything else. And there's been a lot of talk in the industry about combining X2 and Xpack because they're kind of double redundant. And that never happened, but basically Xpack kind of fell by the wayside, but it's acknowledged. You'll never see it in the networking world. The other big popular one right now is the XFP. So founded March 2002. It is the first of these optics to use a true 10 gig serial interface. And because of that, because of a few other things also, it's a variable speed interface, so you can make it talk to a lot of different systems. And because the 5-framer has been offloaded, you can now make this thing talk to multiple systems. So you can take the same optic and plug it into an OC192, into a 10 gig, into a 10 gig fiber channel, into transport gear, and it'll just work. And it's also right now one of the most commonly deployed optics. You could debate as to whether it's more popular than Zenpack or not, but it's certainly getting up there, and it's certainly rising faster than Zenpack. And it has a full support of exotic optics. You can do full 80-kilometer reach. You can do full DWDM. In fact, it's even cheaper to do DWDM on this than it is on Zenpack. The only limitations are limited CX4 and no LX4 technology, and I'll talk more about that in a bit. But it's very popular, and it's actually a huge power savings as well. So you can do high density on these cards. And then the brand new one that a lot of people are just now starting to see with the announcement of the Cisco Nexus platform and a couple other things that are coming later this year is the SFP Plus. And basically this is an evolution on the original SFP. It's physically the same dimensions, it's the same 20-pin connector, but obviously it's very different internally. And the main goal here is to extend the multi-rate support all the way down to do 8 gig fiber channel. So in theory, what the goal for this is to be able to build a slot that will take either a regular SFP and do 1, 2, 4 gig fiber channel, or take SFP Plus and do 8, 10 gig fiber channel. And that's not required by the spec, but it's something that could be done. So that's part of the draw. And also, this is a little bit smaller than XFP. It's about 30% smaller, which is not a huge amount. XFP was already pretty small. But basically, they offload the CDR functionality. I'll talk more about that in a bit. But expect the target market to be fiber channel enterprises and very high density 10 gig. So here's a quick summary of the characteristics. And when I say max ports per blade, you can obviously go higher than this, but this is kind of what it was designed for when you take into account thermal properties, heat sinks, whatnot. You can stuff these things in a little bit higher. But that's the general overview. So now to dig in a little deeper here. So I wanted to start by talking about some of the 10 gig pluggable component technology. So when I say PHY, that's a physical layer component, and it's broken down into 3 subsections: the physical coding sublayer, the medium attachment sublayer, and the physical medium dependent sublayer, which is basically the framing and coding. And then you get down all the way down to PMD, and you're talking about what type of laser am I using to fire over this particular type of fiber to go this particular distance. SERDES is a serializer, deserializer, and it basically just converts between multiple parallel signals and a single serial signal. And the CDR is the clock and data recovery chip, which is almost an analog thing. Just think of it as retiming and signal conditioning on a chip. So the 10 gig PHY comes in 3 major variants, but two variants as far as serial and parallel. The first 2 variants are the 10G base R and W, which are the LAN and WAN PHY versions of a true 10 gig signal. And they also implemented a PHY that runs 4x low speed 2.5 gig signals to achieve the same thing. And there's a few advantages to doing this. If you're transmitting a lower speed signal, it's easier as far as the electronics are concerned to transmit and receive the signal cleanly. It requires less work, less technology. But you also have to take into account the multiplexing, and that's going to add a SERDES. That's going to add potentially, in the case of optical, a small optical mux. There's basically 2 implementations of this. One for optical is LX4, which is 4 wavelengths of light, roughly not standard CWDM, but roughly the same kind of spacing as a CWDM product. And there's a little mux built in, so it just transmits 4 different colors of light out the fiber. And it works great for sending 4 low-speed signals. And on copper, the variant of this right now is CX4, which is a proprietary cable or an InfiniBand cable, but it's 4 parallel paths over copper, so same concept. Strangely enough, the way that the pluggables themselves interconnect to the backplane have the exact same choices as to whether you want to do 10 gig serial or 4 parallel lanes. So the two main interconnection technologies that you'll see are XAUI or XAUI, which is 4 by 3.125 parallel channels. And the reason that it's 3.125 for a 2.5 gig channel is it's 8B10B encoding. So you've got a significant amount of overhead. And the other major one is XFI, now SFI, which is roughly the same thing, which is a single channel of around 10 gigs. And for example, if you take a 10 gig E signal, it's got a much more efficient encoding method. So your overhead for 10 gig is only a few percent, so 10.3125. And every time you have to do the conversion between these two, it requires a serializer deserializer. And every time you add one of these, it increases the cost of your component, it increases the heat and the power, and consumes board space. So obviously the ultimate goal is to match technologies. If you have an optic that transmits 4 parallel lanes and you have an interface bus that uses 4 parallel lanes, connect the dots, it's really easy to implement. When you have to go between the two, that's when it starts becoming problematic. So optimal configuration is XAUI talking to something that's 10G base X, or XFI talking to something that's 10G base R or W. And the suboptimal configuration is obviously the mismatched version of that. So when you have, for example, XAUI, which is the older technology, talking to 10G base R, for example, you know what, if you've got a big Zenpack, there's plenty of room to fit the chip. If you've got a much smaller XFP, not so much. So that's why you tend to see very, very little in the space of going the opposite direction, but you see lots of Zenpacks that are 10G base R. And as far as what's going to end up happening with this technology, the original implementation of it was a way to take advantage of the technology at the time, and that was great. For example, 10G base LX4, you could stick it on single mode and get 10 kilometers, the same as LR, or you could stick it on FIDI grade multi-mode and get 300 kilometers. So it has place. But what you're tending to see happen is there's new technologies that are being developed to replace these things. The big one right now is 10G base LRM, which is long reach multi-mode, which lets you go further than SR. SR is okay if you're doing stuff in the same rack or if you've got high grade multi-mode fiber, but most people that have to run 10 gig over multi-mode fiber don't have high grade multi-mode fiber. They've got the old crappy stuff. So LRM is going to be a viable option for doing data center cross connects that SR can't handle right now. And the replacement for CX4 and copper is going to be 10G base T, which is longer reach and lets you use your existing Cat5, Cat6 infrastructure, so you can now run this potentially through a wiring closet instead of just with your weird custom cables. Uses the good old RJ45 connector. So you're going to see the 10G base X stuff kind of start to fade away eventually. So when I was talking earlier about whether the Phi framer was on the pluggable or not, this is what I mean. Basically, there's a big advantage if you take the framer, the physical layer framer, off of the pluggable itself, and that lets you make the pluggable protocol agnostic. So you now have the same pluggable that you can use for 10 gig LAN or WAN Phi. You can use it in OC192. You can use it in 10 gig fiber channel, and you can even use it in transport networks that are doing forward error correction. I think Juniper announced a few days ago that they are now doing forward error correction framing off of their 10 gig PICs on T-Series. So that will let you, for example, potentially take what used to be an 80-kilometer optic and now maybe get 120 kilometers out of it just by a little bit of software coding. So it's great technology, and being flexible and being able to implement that on the framer without having to upgrade your optics or to be able to implement different versions of FEC is a good thing. And obviously it allows component reuse, which is great. Another big advantage of the protocol agnostic versions is it tends to be much better if you're doing 10 gig WAN Phi. It's kind of what happens if you do it on the If you do it on like a Zenpack or an X2 or something like that, because the framer is on the pluggable, you have to go out and buy the special pluggable. And typically the cost tends to be significantly higher, in the order of 3 to 4 times the list price of the LRs to get an LW. And you're also never going to find anything outside of an LW. You're not going to find an SW. You're not going to find an EW. Best of luck trying to find a ZW. The people don't make these things. In theory, there might be like one EW floating around the world somewhere. You can go chase it, but it's problematic. So if you've got a neutral pluggable, you can insert it into any host which supports WAN 5 and now use any particular optic you want. And the other version, the other difference is when you implement this on Zenpack, there's not a good mechanism for talking about what's happening at the WAN 5 sublayer to the host. So you end up calling someone's NOC and saying, my circuit's down. They say, what alarms are you seeing? And you say, my link is flapping really fast. Basically, they laugh at you for 30 seconds and then they hang up. And even if you're working with a carrier who can deliver 10 gig LAN PHY, a lot of the people are not trained in this. So it tends to be much better from a support perspective if you're capable of running a true 10 gig WAN PHY over WAN optics. That lets you lower your cost, and the overhead is minimal, and it really lets you improve your support and your quality of your network. And you get all of your access to your silent alarms and path trace and whatnot. The other kind of evolution that you see on these optics is more offloading of the optics to make them smaller, use less power. And the new one that's come up with SFP Plus is to offload the CDR. And the only advantage of this is, yes, it does make the pluggable smaller and it uses less power, but it actually has a lot of disadvantages as well. At the end of the day, you're not actually removing any components, and you're not really optimizing any components. You're just kind of moving them around. So yes, you've made the pluggables take less power, but you've just moved it to the board. So it doesn't really help that much. And it also, a lot of the CDRs, you want a different CDR for different functions. If you're using a 10 gig SR or short reach optics, you may not carry. You may never have to do clocking recovery. It may just never be a problem for you. If you're now running this over 80 kilometer DWDM, it might be a much bigger concern. So you might want a higher quality type of thing. Whereas if that's been moved to the board, you're going to be very limited in what kind of reaches you can get. And also there's a lot of advancements in things like electronic dispersion compensation technology, where you might be able to end up removing the the 50 kilometer spool of fiber that you have to kind of undisperse all of the wavelengths. You get the slope back. So you're cutting yourself short if you've offloaded all of these components onto your board, because now you've got to upgrade this entire board. So here's kind of a little graph of here's kind of the evolution of the power classes, and you can see the Zenpack and X2 and XFP. It's been going down over time, but what you see happening here, so there's different power classes. Like a class 1 might be a copper or a SR or an LR. Class 2 might be a 40 kilometer ER. Class 3 might be an 80 kilometer ZR. And what you kind of see here is, along with the dropping of power, which is you're getting down pretty significantly by the time you hit XFP, but when you go to SFP Plus, what you see is they haven't really reduced the power of the class 1. They just kind of chopped the top off. So SFP Plus was designed under the premise of doing high density short reach, but chop the top power class off, and now you don't have enough power to power a long reach optic. So it's problematic. Here's a quick little comparison of the different types of optics available, and this is mostly just for people to look at later. So there's also the software side of pluggables to talk about. So pluggables talk to the host via a low-speed control bus. That's a lot of commands like power up, power down. There's diagnostic information, loss of signal, whatever. There's the big one, which is the digital optical monitoring, which is great when you're troubleshooting layer 1 issues, because you can now see what the power is on a particular circuit that might be going bad without having to dispatch a tech and train them how to work a light meter. But the other side effect of this is that these things are now capable of reading EEPROM data, and that includes things like optic type, vendor name, and vendor name becomes important. So I will disclaim the next couple slides on 2 points. Number one, I'm going to pick on Cisco a little bit, but that's just because if you believe the analysts, Cisco is 70% of the 10 gig pluggable market, so they're the easiest target to pick on. And number two, I will say that I don't blame Cisco for what they're doing. It's, they're in business to make money, and if any of us as service providers had a way to twiddle something in BGP to make our customers not use Cogent and make us $1 billion a year, we'd all do it too. So. The key facts on this particular issue: no major networking vendor makes their own pluggables. Not one. There's no foundry manufacturing for pluggables. There's no Juniper. There's no Cisco. There's no Extreme. There's no nothing. Pluggables are made by Finisar, Intel, MCore, Agilent, Opnex, Hitachi, JDS Uniphase, a variety of other people, but folks like that. And because these EEPROMs are programmable, it's possible for anyone to have a store brand optic. So Cisco can order up their optics that say Cisco on them, and no one knows it says Cisco. And there's also a significant market in doing this, and there's been some analysis on the numbers, and it's basically come out that Cisco in fiscal year 2006 made $1.4 billion in profit from reselling pluggables. That's not revenue, that's profit. So there's a huge incentive for vendors to keep customers locked into one particular source of optics and not let them wander around or buy cheaper. So how do vendors keep customers locked in? Basically psychology. So you start with the obvious, fear, uncertainty, doubt, which is if you don't use these, you're going to get some kind of inferior knockoff. We test ours to a higher standard. Something like that. The other one is if you put this in your router, it'll blow up, it'll melt down the data center, everyone's going to sue you, and we're not going to support you. And the next one is, you plug this in, all of a sudden you voided your support contracts, and now it's going to be a huge hassle because something else is going to break, and we're going to say, oh, no, not our optics, you're screwed. And there's also a huge financial component to this, which is there are a lot of people that are making pluggables, and there are very few buyers. If 70% of the market is controlled by Cisco is buying 70% of the optics. They're able to dictate the terms. They're able to say exactly what specifications they want. They're able to set the price, and they're able to pay very low prices and keep these things from being resold outside of that. And if they can't get it done that way, then what ends up happening is they resort to vendor locking, where they just say, if it's not our brand, disable the port. So there's been some evolution in vendor locking lately. It's been going on for a while. It's been going on since the 1 gig days. There's been a lot of customer outrage over it. Basically, people get up and complain, throw things, and say, I'm not going to buy from you if you do this. And so at the very least right now, almost everybody has at least a hidden command to disable it. A lot of vendors are kind of waffling on the issue, but they're still saying we're going to support any kind of optic. And professional counterfeiters are not really being deterred by this. What you see happening by using vendor locking, you're preventing people from competing legitimately. If you're an optical manufacturer, you've produced an optic, you can't sell it to anyone in this room. You have to sell it to Cisco. And Cisco is going to mark it up 10 to 15 times and resell it and make all the money, and you're going to get screwed. Well, what are you going to do about it? The only option that you have is to start counterfeiting Cisco's. And once you go down that path, you no longer have a brand to protect. You no longer have to say, my brand is superior, I'm good, I'm promoting myself. You can now churn out cheap, sloppy knockoffs. And these things end up getting into the VAR supply chains, and people end up buying these optics without knowing about it. So it's not really helping in that front. And basically the latest news as far as vendor locking on the 10 gig pluggable front is feature impairment, which there's been a few people that I've asked about this specifically, and they said, well, we'll never be able to say, if you don't use our branded optics, we're going to disable the port because it pisses the customer off. But what we can do is say there's certain features that only our optics are going to do. One of the big ones seems to be DOM. So there's been some intentional disabling, or there will be some intentional disabling in some vendors in new code of those features. So quick review at the end to wrap this up. Basically, what format is right for you. So if you're considering Zenpack, the advantages are there's a huge established base. You can buy them anywhere. It has the best selection of long-reach and DWDM, and that's quickly being eclipsed if it hasn't already been by XFP. But it also has full support for LX4 CX4. So if you've got a lot of legacy multi-mode fiber to deal with, or if you've got a lot of short reach stuff and you can get away with copper, it might be for you. The disadvantages, obviously, it's very large, draws a lot of power, so you're really not ever going to see more than 4 ports on a blade. And it is not protocol agnostic, so you're going to pay more for WAN-Fi, it's going to be less friendly to use, and this is not the lowest cost solution. So it still has its place, and we're never going to see Zenpack go away, but it might not be the best thing to buy for a new deployment right now. The other big one that's being pushed is X2. Obviously, it's smaller than Zenpack. It has lower power requirements. And it's very easy for people who are manufacturing boards that use Zenpack to use X2 because they don't have to change any ASICs, they don't have to change the way the board is really designed, they just move a few components around, packing a little higher density. It's roughly more of the same. It has full support for LX4, CX4 technologies, and it's being pushed by Cisco, which might make it catch on, who knows. But yeah, all the new stackables, 6708, 6716, are being developed as X2. The disadvantages right now, there's very little deployed base. There's very few sources to get it from, and there's very little in the options of long reach, exotic optics, etc. And not that there's ever anything that's going to prevent that, but it's just a matter of customer demand, and right now there isn't any. And basically it has the same other limitations as Zenpack. So if you have to pick, that should say the worst of both worlds between it's the worst of all the disadvantages and none of the real advantages. So XFP, big advantages are there's a large deployed base. They're cheap and easy to find. There's a whole lot of people that have these out. There's a lot of technology coming out in the form of LRM and 10G based T that are going to replace LX4, CX4. So you might not need those Zenpacks anymore. The power and density are actually very good. The actual power difference between an LR on an XFP and an SFP Plus is minimal. So if you really wanted to design a high-density XFP board, you could certainly do higher than 16 per slot, but you would have to draw a limit with different power classes. It's protocol agnostic, it's easy to spare, better for WAN-Fi, and it actually is the cheapest option right now for DWDM. The disadvantages, there's no LX4 for it, and somebody actually came out with a CX4 for it, but the connector is bigger than the pluggable itself, so it's kind of ugly. And you'll never be able to get 48 port blade densities out of this, so just something to think about. And SFP Plus, which is the new one to consider. Big advantage, extremely high density. You can do 48 port per blade just fine, or 32 or whatever. Physically, it's the same as SFP, so you've got a physical format where you could support the old style and the new style in the same thing. And you might be able to build an extremely low cost 48 port 10 gig box and deploy it everywhere, the infamous Google switch, whatever. The disadvantages, there's a hard cutoff on the power budget. So theoretically, physics, there's nothing that prevents you from being more efficient, but in terms of practical deployment right now, what you're going to see is that when Cisco ships the Nexus, it's not even going to have support for LR. You've got SR. You'll be waiting a while. Eventually, LR will come out, but you're never going to get 40, 80 kilometer. You're never going to get long-reach DWDM stuff out of these boxes. So if you're deploying these boxes and you ever expect to get that kind of functionality, you might have a problem. So it's not inherently bad, but it's not a full replacement for XFP and probably won't be. So here's some further reading if you want to read up on the standards of these things. URLs, just read the slide. And questions?
Thank you. I will take one or two questions. No? Martin, can you come and set up? Thank you very much, Richard, for a very comprehensive presentation.